Hello everyone, and let's go ahead and start this final lecture of what is Chapter 8 that I have labeled in Conservation of Energy. This lecture picks up from other lectures that I have, and here I'll be discussing the conservation of energy for a calculus-based Physics 1 perspective using not only mechanical energy but also non-conservative forces. Okay, so let us get started. Okay. So first, I want to review the conservation of energy. And that is, in cases with no friction, we know that, say we drop a book, the change in the kinetic energy of the book plus the change in the gravitational potential energy should be zero. We could also say that the change in the kinetic energy is equal to the opposite of the change in the potential energy, because the kinetic energy is increasing as the gravitational potential energy is decreasing. But since their overall change of both is zero, you could say that the initial quantity of K and U and the final quantity of K and U summed together, that has to be a constant, that its initial K plus U, and U being the potential energy, is equal to the final amount. And in fact, if you write out that situation, you'll see that we can define what we call mechanical energy, which is kinetic energy plus potential energy. And the mechanical energy can be defined when there are conservative forces, and the mechanical energy is conserved in the absence of non-conservative forces. Okay? So one thing I should say is that note that many of these conservation of mechanical energy equations are going to be independent of mass. Notice that mass is in all the terms, and the mass will cancel. Another example of a conservative force is not just gravitational force, but the Hooke's law spring force. That is, the work done by a spring only depends upon the initial and final positions of the spring. Imagine we take a mass that's attached to a spring on a frictionless surface, and we compress it so that the spring is compressed a distance x from its equilibrium starting position. If we release the block after the spring is compressed, we originally did work, that is, we put a force over a displacement on the mass to compress the spring, and since we put work in, then we had to store potential energy. That's because we see it results in kinetic energy. So we recall from an earlier lecture that the work done by the spring is 1/2 kxi squared plus 1/2 kxf squared, where xi and xf are the initial and final positions of the spring. Notice that given that the final position of the spring is 0, in this case, x is just going to be xi, because that's how much the spring was originally compressed. And by the work kinetic energy theorem, the kinetic energy of the block is equal to the work done by the spring, and that's 1/2 kx squared. So what we can say is that the elastic potential energy, sometimes called the spring potential energy, is going to be this quantity 1/2 kx squared, which is an important quantity. That is, anything that elastically deforms and has spring properties that obeys Hooke's law should have 1/2 kx squared as its potential energy quantity. Moving on from there, here's an example to show how an energy diagram is set up for a mass that's oscillating with a spring on a frictionless surface. Okay? Notice that when the mass is first fully elongated, the potential energy is equal to the total energy. The object is initially at rest when elongated. When it starts to move back towards equilibrium position, it has some velocity which is negative on the x-axis. Notice the potential energy has gone down and the total energy remains the same, so the kinetic energy has to increase. And that's because the object is moving. When the mass moves through equilibrium position, we have all entirely kinetic energy because x is 0 and 1/2 kx squared is 0. The total energy still being the same, but the potential energy being non-existent momentarily. As the mass continues to compress, so via inertia, it overshoots the equilibrium position, and the kinetic energy now starts to decrease because we start to build up elastic or spring potential energy once again. The total energy remaining constant. Notice that 1/2 kx squared is positive because k is a positive number by convention for the spring constant, and then x squared will always be positive or 0. So spring or elastic potential energy is a positive definite quantity. I will perform this example in a later video, so let's move on. How about non-conservative forces? The mechanical energy is removed or added. Now when I say removed or added, it's energy that comes from external to the system. In other words, if there's, let's say, a force that removes mechanical energy, that means the total energy of all systems is still conserved. It's just that the energy many times goes into a different form, let's say heat. Or let's say we add energy to the system. Maybe we push on the object. You can imagine that we are, let's say, external to the system of the object, so we add mechanical energy to the system, but that's only because we are external. And so, again, the energy came from us from some other source. Now, the work depends upon the path when we talk about non-conservative forces. Here's an example. More work is done by friction on the brown path as opposed to the blue path. Since the path is longer for path A, path B being shorter, we still get from point A to point B. The longer the distance over which, or you might even say the path that the friction can act over, the more opportunity we have for rubbing and then also loss of energy via non-conservative work done by friction. You could also imagine if a hand pushes on the book, that would be, again, a non-conservative force because basically hands are external to the system. Okay, so mechanical energy is not conserved in a non-conservative system, but the total energy is. As long as you define the system to include the object or substance, so to say, that's performing the non-conservative work, the total energy of the system is still conserved, but that means the change in the kinetic plus the change in the potential energy plus the change in the internal energy is 0. So for friction, say kinetic energy goes into internal energy. Via rubbing, let's say the object that's performing the friction gets warmer. So a lot of times if a block is sliding across the table will get warmer. When you push objects, the internal energy goes into kinetic energy. Imagine if we, as an applied force, are using our metabolic energy, we can increase something's kinetic energy. Now the details of that, the details of how much does the temperature change via friction, or how much does internal energy go into kinetic energy via non-conservative forces, say by external agents like us, people pushing on systems, that's beyond the scope of this course and certainly beyond this lecture. But you could study that in detail somewhere else. Work done by non-conservative forces changes the mechanical energy, and if you consider work, the work done by non-conservative forces will either be positive or negative. So you could consider either a change in internal energy or a work done by non-conservative forces. So do the calculation one way or the other. Many times if you're looking at something like friction, that a lot of times we say takes energy away from the system, you either make this a negative non-conservative work because it's taking mechanical energy away during the motion, or you would call it a positive increase in internal energy on the right-hand side that's at the final stage that results from rubbing. But don't use it both ways. It's either negative non-conservative work, that is for those of you that consider yourselves pessimists, you like adding in negatives, but those of you that like to think about pouring energy into containers, go ahead and make the positive change in internal energy, that increase of heat on the right-hand side, final, when you perform these conservation of energy equations. So this example will use those equations which we were just discussing, and I will perform this in a later video. Same with this example, number 3. Okay, the last thing I want to discuss in this chapter and in this lecture is the potential energy of conservative forces. We know that change in kinetic energy plus change in potential energy equals 0. And let's focus in on gravitational potential energy here. We know that the work energy theorem says that work is the change in kinetic energy. So as long as we have conservative forces, the change in, let's say, gravitational potential energy is equal to the opposite of the work done. Notice that you can derive the relationship then between force and potential energy. We know that work is like force times a displacement. And we also know that gravitational potential energy is something like joules. So what that means is we can then instantaneously change the gravitational potential energy, and there's a minus sign, and if we change it in a direction of interest, if we change it in the direction of interest that changes the potential energy most rapidly, namely the gradient direction, namely the direction where the potential energy will go down most, then we would have a force. And that force in the x direction is minus du dx. And du dx here means the derivative of the potential energy function with respect to x. Okay? So, by the way, in this course, we'll often just perform one-dimensional derivatives. So the force is the negative of the gradient of the potential energy function. In 3 dimensions, so like in a vector calculus class, you would say that the force vector in all 3 dimensions is minus the gradient vector of the potential energy function. So in other words, forces cause objects to go down the potential energy gradient. Okay? Now for gravity, the potential energy function we know to be mgy, if y is a vertical axis. So if we calculate Fy, which is very similar to this equation just because it's a one-dimensional force and it's the negative gradient of the potential energy function, then that's going to be minus d by dy of mgy, and that gives you minus mg, which makes perfect sense because the gravitational force should be minus mg if the positive y direction is directed upward. So notice that what we often say is we say balls go downward towards the center of the earth. That we know from forces. But another way to say this in terms of energetics is that balls go down gradient. In other words, when you release a ball and it's in free fall, it goes straight down towards lower and lower values of potential energy. That's sort of its natural conservative force behavior. So I also want to introduce this idea of stable equilibrium versus unstable equilibrium. A stable equilibrium is when an object is in equilibrium and you perturb it. That is to say, you displace it from its equilibrium position. It comes back to its original equilibrium position. Watch out for the boulder that comes back. But the idea is that, notice when you're at the bottom of a valley, so to say, the idea is that the restoring force, that is the force due to potential energy, if the displacement is positive, that is x is to the right, the force is negative. It brings you back towards x equals 0, which is the equilibrium position. If the displacement is negative and the force is positive, it also brings you back towards equilibrium. Now how about an unstable equilibrium? Suppose you're on the top of a hill and you perturb the object. If you perturb the object, it never really comes back. That is, if x is positive, the force is positive, and the object just keeps going away. It does not come back to x equals 0. If x were negative, the force would be negative, the object would also roll away. So effectively, bottoms of valleys in terms of gravitational potential energy are stable equilibria. Tops of mountains are unstable equilibria points. And we will actually see this if we plot capital U versus X, the potential energy versus the displacement position on an axis, we'll see that stable equilibria points looks like so, and then unstable equilibria points look like so, where we have the bottom like a local minima of U or a local maxima of U. Okay, so since the force is minus du dx, we can sketch out those energy diagrams. So consider the potential energy of a spring. Notice that 1/2 kx squared is a parabola, and that parabola has a certain shape depending upon what k is. If you recall an earlier intuition video, when k is larger, the parabola has greater slope. Remember, it slopes up more rapidly, but that's because the coefficient in front of the x squared is larger. Well, we can say that if a spring, let's say, is elongated to x max, or then compressed back to minus x max, spring with a mass on a frictionless table, notice E here is the total energy, but notice that the potential energy equals the total energy when the spring is maximally elongated or maximally compressed. That is, when it's at rest. But notice we can also get some information about the force here. That is, the slope on the left-hand side here is negative, but the slope of the U versus X graph would be du dx. If we put a minus sign on that, that gives the force. So the force is going to be positive because a negative slope, that's du dx, gives, with a minus sign, a positive force. So the Hooke's law spring force, the restoring force, should push the object back towards equilibrium. Whereas, when you're on the right-hand side and x is positive, the force should be negative, and that should push you back towards equilibrium. That's because the slope is positive, the force is negative by this equation. So this should be a stable equilibrium point. That is, when the slope is positive on the right-hand side here, the force is negative, because when x is positive, then we know the Hooke's law spring force, the restoring force, should be to the left. It should be negative. Okay? So notice that the total energy is conserved. That's this line. That's kinetic plus potential. So note that the kinetic energy of the block will be exactly the same thing as this total energy line, and then you subtract off this potential energy curve at any location, and then this measurement right here exactly is the kinetic energy of the block, the distance from this E line to the orange curve here. Here's another example of a potential energy versus x, but again, this is like the top of a hill, especially if it's gravitational potential energy. If x is negative, the slope is positive, and that's going to be a negative force, cause the object to keep moving away from equilibrium. And if the x is positive, the slope is negative, but that's going to mean the force is positive. So this is an unstable equilibrium point. Again, I will perform this example in a later video. Okay, so that concludes this lecture and concludes Chapter 8 slides. Thank you very much for your attention. Please smash that like button on this video. Please subscribe to the channel, and I will see you in the next video.